All right, everyone, welcome back for another week of Earth Science. This week we're going to be talking about earthquakes and volcanoes. So, our goals for this lesson are first to understand how and why volcanoes are formed, then we will explain the processes behind earthquakes, and then we will evaluate the risk to people from these kinds of tectonic events. So that's the overarching theme for this week is processes of plate tectonics that present hazards to people. So let's start with our volcanoes. So volcanoes are simply where molten rock from the asthenosphere comes to the surface. And that molten rock is called magma when it's underground. It's called lava when it reaches the surface. Two names for the same thing, just depending on where we are encountering it. And the type of eruption that we get from a volcano, right, when this molten rock actually comes to the surface, can be in two basic types. And of course, you can have mixtures or things in between, but there's two basic types of eruptions that you might get. So one type of eruption is what you see in the upper photo, which I'll move out of the way of a bit there. That's Mount St. Helens in Washington State, erupting back in 1980, one of the most famous volcanic eruptions within the United States. And you'll see what's happening there is this, gigantic cloud of ash just blasting upwards into the atmosphere from that volcano. So it's a very explosive eruption. And in fact, that's the term for this kind of an eruption, explosive eruption. And this happens when the materials in that magma are very viscous. So they're very thick. You can think of them as being closer to like tar or honey rather than like a thin, watery kind of consistency. And so this is a product of the specific chemical composition of this material. And we're not going to get into the details of, which chemical elements and so forth make this up. But if it has this thicker consistency, it's going to trap a lot of gases. You're going to get a lot of gas bubbles trapped in there. And so that's going to give you this really explosive kind of eruption when it finally reaches the surface and the pressure is released and the gases will just sort of blow everything sky high. The other type of eruption is what we call an effusive eruption. And that's what you see in the lower picture. That is Kilauea, one of the volcanoes in Hawaii. And you see there that as the lava is leaving the main vent, the main spot that it's coming out of, it's just kind of flowing like a river down the side. It's not blasting into the sky like Mount St. Helens. Because there we have a less viscous, a thinner kind of consistency to that lava. So the gases have mostly escaped from it. And so it's now just flowing downhill in this kind of eruption. So we have these two different kinds of eruptions that are going to happen from different sorts of volcanoes. So here in the picture, you see a diagram of the internal structure of a volcano. So with a volcano, we've got the mountain that's formed from all of the erupted material that has piled up from past eruptions. And so deep underneath it, we have the magma chamber. So that's where the magma is gathering, right? Magma is coming up from the asthenosphere and it is kind of pooling underneath the volcano. And eventually you get enough magma down there exerting enough pressure that it will erupt. It will come out to the surface through one or more of these vents. So you see the main vent running up the center of the volcano there. So that magma will come out through the top of the volcano. But then you also see this volcano has a couple of these side vents where some of the magma is going to come out through another crack in the side of the volcano. So one volcano can have multiple of these vents, lava and other materials coming out of different parts of it, right? And so then that eruption is going to be some combination of this less viscous lava flowing down the sides or these ash clouds and cinders being blasted up out of the top of it. And so depending on which kinds of eruptions our volcano is having, the volcano itself, the actual mountain, is going to have a different sort of structure. So one type of volcano we might get is what we call a shield volcano. So a shield volcano is our largest type of volcano in terms of just the size of the overall mountain that's created. But it's also our most gently sloping volcano. So the name comes from the fact that it's kind of the shape of like a medieval shield, like imagine like a Viking shield if you set it flat on the ground, right? It's very wide and it sort of arcs up very gently in the middle. That's kind of the shape of a shield volcano because it's mostly produced through those effusive eruptions. So you get this lava flowing out the top, and because it's very thin, it can flow very easily. It's going to really spread out, and so it's going to give you this very large but not very tall kind of volcano. So that's a shield volcano. On the other end of the spectrum, if you've got a volcano that has mostly explosive eruptions, you're going to get a cinder cone. So that's going to be a much smaller and much steeper volcano. So you're going to get this small, steep pile of cinders, ashes, and other materials that are that come blasting out of this volcano with these explosive kinds of eruptions. Then in between those two, you get what's called a composite volcano or a stratovolcano. So strato is from the Latin for layers. And if you were to cut into one of these volcanoes, you'd see layers of different sorts of material. And that's actually what's illustrated in the picture there. So that picture is of a composite volcano. You'll see it has those different layers inside of it. So this is a volcano that alternates the different kinds of eruptions. So it will have some explosive eruptions that pile up sort of a steep cone of material, and then it will have some effusive eruptions where lava just runs down the side of it and hardens into a lava layer over that. And the alternating of these two kinds of eruptions allows our composite volcano to be larger than a cinder cone because you have the lava hardening to stabilize the material, but then also steeper than a shield volcano because you have this explosive material that's piling up higher than lava could pile on its own. So you get a volcano that's in between in size and in between in shape in terms of the steepness of the volcano because it alternates types of eruptions. Another important kind of landform that we get associated with volcanoes is a caldera. So this isn't sort of a distinct type of volcano, but it's a thing that can happen to a volcano. So you've got that magma chamber down under there, right? That's where the magma gathers until there gets to be enough of it and enough pressure to cause an eruption. If that magma chamber essentially completely empties out and you've got this void underneath your volcano, the top of the volcano can collapse into that magma chamber. And so that leaves you, rather than just a small vent hole at the top of the volcano, you get this giant crater in the top of the volcano. We call that a caldera. So when you see a crater formation on the Earth, sometimes it might be a crater from like a meteor strike, which would be a totally different kind of landform. But if it's created by volcanic activity, it's a caldera. It is the top of a volcano that has collapsed down into the empty magma chamber. And if that volcano were to become active again, if more magma were to accumulate, then you might actually get a crater with a smaller volcano forming inside of it. That's what we see in a place like Crater Lake in Oregon. We have a big round caldera that has filled up with water from a collapse of a much larger volcano in the past, but then there's a small island in the middle of Crater Lake where the volcano is reforming at the center of that caldera. So here's a map of the world showing where active volcanoes are located. So all the little red triangles are volcanoes that could potentially erupt. They're of course not all erupting right now. Some of them have not erupted for quite a long time. So for example, the one volcano you see there in the southern part of Australia, that last erupted about 6,000 years ago. So it's not something that we're terribly worried about it erupting again today, but it could. You know, it's not completely extinct, so they've marked it on the map. And so as you look at this map, you may start to notice a few patterns. You may see a few things that jump out at you about the locations of these volcanoes. And so we're going to talk about where volcanoes are formed, and we'll flip back to this map to show how these things can be seen on the surface of the Earth. So one common place we get volcanoes is at convergent plate boundaries that involve subduction. So if you'll remember from our last lesson, when we have two ocean plates coming together, or even ocean and a continental plate coming together, an ocean plate will get pushed down underneath the other one, and we call that subduction. And when you have subduction, the plate that's getting pushed down into the asthenosphere is going to melt. And all of that melted rock is going to be less dense than the rock that forms the asthenosphere, so it's going to try to come back up to the surface. And so we are going to get volcanoes forming. And if the subduction is going underneath an ocean plate, we get volcanoes forming on the floor of the ocean, which eventually might stick up out of the water as a arc of volcanic islands. If it's being subducted underneath a piece of continental crust, then those volcanoes will form on the continent. We'll get a volcanic mountain range. And so we can see that in places like the Aleutian Islands up here near, or coming off of Alaska. We've got a arc of volcanic islands where we have some ocean-to-ocean convergent plate boundary happening, and then likewise down into Japan, and then down to the Philippines. We've got a lot of ocean-to-ocean convergent plate boundaries there. That's also what we see in the Caribbean islands, which are volcanic due to ocean-to-ocean convergent plate boundaries. Then we've got some ocean-to-continent convergent plate boundaries in places like the west coast of the Americas. Both North America and South America have mountains along their western coasts because we have ocean to continent convergent plate boundaries happening there, and those mountains are full of volcanoes. You've got things like Mount St. Helens that we already looked at is on the west coast of North America. It's the result of the subduction underneath the North American plate. So that explains a lot of our volcanoes here. Most of the areas where you see big strings of volcanoes on this map are due to subduction, due to a ocean-to-ocean or ocean-to-continent convergent plate boundary. We don't get volcanoes at continent-to-continent convergent plate boundaries. Let me flip back here. So if you look at the Himalayas, for example, between India and China, you see basically no volcanic activity there because there's no subduction happening. We have these two continental plates, they're ramming into each other, and they're pushing up some really gigantic mountains. They're creating the highest mountains in the world today. But because neither of those plates is being pushed down into the asthenosphere, you're not getting melting of that rock, and so you're not getting any magma coming up to fuel extensive volcanic activity. So the continent-to-continent convergent plate boundaries don't create volcanic activity. However, a divergent plate boundary does create volcanic activity. If you're pulling the lithosphere apart, then you're going to get magma coming up into that gap, and it's going to come up in the form of volcanoes. So you can see that at places like some of the mid-ocean ridges. You've got volcanoes in the center of the Atlantic Ocean, where we have the mid-Atlantic ridge, divergent plate boundary separating Africa and Europe on one side, the American plates on the other side. As they pull apart, you get volcanic activity happening in that gap. You can also see a whole lot of volcanoes in East Africa, and that's the East African Rift Valley that we talked about last time. So there you've got the continent of Africa is starting to split apart. Eastern Africa is starting to pull away from the rest of Africa, and so as that divergent plate boundary happens, as that plate starts to split, you're getting volcanic activity coming up into essentially into the gap that's forming as the plate is separating. So most of our volcanic activity is happening as the result of these kinds of tectonic plate boundaries. But we have one more important type of volcanic activity, which is what's called a hotspot. So at these different kinds of plate boundaries, we have magma coming up out of the asthenosphere. But we can also have a plume of magma coming up out of the asthenosphere just at kind of a random spot. We don't 100% know exactly why hotspots occur where they do, but we know that they're a thing. We know that they happen, and they may be happening just in the middle of a plate. They may be very far from any sort of plate boundary, but we get this plume of magma coming up out of the asthenosphere. And as it rises, it's eventually going to basically punch a hole through the plate and create a volcano there. So this plume of magma breaks through the plate and creates a volcano. Now, the interesting thing about a hotspot is that the hotspot remains in place. It stays in the same spot on the Earth. but the plate that it is creating the volcano on is still moving. And so what we get when we have a hotspot is we get a chain of volcanoes in which the volcano at one end of that chain is active. And then as you go down the chain, you get inactive and extinct volcanoes that get older and older and older. So in the diagram there, you see one of the most famous hotspots in the world, which is the Hawaiian Islands. And so right now in Hawaii, you have active volcanoes just on the Big Island. And so in the southeasternmost part of Hawaii, you have the Big Island, the island of Hawaii, and it's got several active volcanoes on it that experience eruptions regularly. And the diagram there marks Mauna Loa, Kilauea, and then Loihi, which is sort of the newest volcano forming just off the coast of the Big Island of Hawaii. So those are the only volcanoes in Hawaii that are really still active. And they've been going, as the diagram says there, since about 0.7 million years ago. So 700,000 years ago, these volcanoes began to become active. But then if you go down the Hawaiian Islands, so the next island you come to is Maui. And so Maui is about 1.3 million years old. So it's no longer active because the plate has pulled it away from the hotspot. But that spot of the Pacific plate used to be right over the hotspot 1.3 million years ago. That's when that island formed. And now it has gotten slid away. So it's no longer getting recharged by magma. And then you go down the line a little farther, you've got Molokai about 1.8 million years ago, Oahu is 3.4 million years ago, Kauai, Niihau are about 5 million years ago. And then as you continue in that direction, as if you continue moving northwestward, you get seamounts. So you get old volcanoes that are so eroded down that they don't stick out of the ocean anymore. But they're there. We can find them on the floor of the ocean. So the biggest island is the one that's being actively built up through volcanic activity, and then they get smaller because they've eroded down. The older they are, the farther they go from our hotspot. And that's just because all of those places were at one point in the past right over the hotspot, having volcanic eruptions, but then the plate dragged that old volcano off of the hotspot. New volcano forms. The old one gets pulled away and starts to erode down. So when you see a chain of volcanic islands that are of different ages, with an active volcano at one end, and then progressively older and more worn down volcanoes as you go down the line, then you're looking at a hotspot. You can also get hotspots on a continent. And so one of the things you'll be looking at in your lab exercise is Yellowstone. So Yellowstone National Park is formed around a set of really interesting geological features like hot springs and geysers and so forth that are the result of a hotspot. There's a magma plume coming up from underneath where the North American plate is currently sitting. So if we get a volcanic eruption, what is it going to do to us? It can do a lot of things to us, most of them bad, but some of them actually good. So if we look at the types of hazards that can arise from volcanic eruptions, the most obvious one, of course, is lava flows. You can have lava, catch up to you, bury the things that you care about, bury your town or whatever. Lava flows tend to be slow enough that people think that they're safe to go walk out to the lava flow and take selfies with it and stuff. That's not recommended because it's real easy to miscalculate the speed of that lava and get caught when you weren't expecting it, and because there are these other types of hazards that can come in that can be associated with the same eruption that's producing your lava flow. So I know there's been a lot of pictures from Iceland recently on social media, people going out to these lava flows and taking selfies and stuff. That's really not generally a good idea. You can also have what's called pyroclastic flows. So this is other material ejected from our volcano. It includes things like broken pieces of cooled off lava. So if you get an explosive eruption, you get all these little droplets of lava ejected into the air, they cool off and harden, and then that flows down the side of the volcano as well. This can be very dangerous material to get caught by or to be in the path of Volcanoes also produce toxic gases. So I mentioned that there are these gases that are in that magma that are released as it reaches the surface. And some of those gases are not real good to breathe in. They can do a lot of damage to you. They can suffocate you if they displace all of the air with oxygen in it that you might be trying to breathe. You can also get acid rain and the falling of ash. So some of what the volcano puts out, rather than flowing down the side of the volcano, will get blasted into the atmosphere. And so that can travel for quite long distances sometimes. And then that material can fall back to the earth. You can get ash piling up on the ground. You can also get the chemicals that are put into the atmosphere can get absorbed by the water in clouds, and so then when that falls back to Earth, you get acid rain because that water has these other chemicals in it, and that can be very destructive when that falls. The picture you see there is the results of one of these ash falls. This is a U.S. military base in the Philippines, and a volcano erupted, and it just buried these buildings in several feet of volcanic ash. And you can see there, especially the main building in the center there, this ash just crushed that building. You know, it was not built to withstand several feet deep of volcanic ash just piled up on top of it. So the fall of this ash can be really destructive and can go often much farther from the eruption than something like lava is going to make it. So it's a much wider area that this can affect. Volcanoes can also start forest fires. You've got all this hot material coming out of your volcano. It can catch things on fire, and then you've got a whole new type of hazard being triggered by volcanic eruption. You've got lahars, which are mudslides that can be triggered by a volcanic eruption. So you're getting mud flowing down off of the volcano that can sweep things away in its path. So you got a lot of really dangerous things that can come out of a volcano. Well, there's one benefit to volcanic eruptions, which is the formation of new soil. So people live close to volcanoes in many parts of the world because as long as the volcano is not actively erupting, that can actually be a really great place to live because the soil that's produced by volcanic activity can be really rich and fertile. The soil is getting new nutrients added to it by this volcanic activity. So you don't want to be right in the path when the volcano actually erupts. But if you come in after the eruption and can take advantage of the new soil built up by the volcano, that can actually be pretty beneficial. So you see large human populations on a lot of these volcanic islands around the world. They're very productive locations. Let's talk about earthquakes now. So an earthquake is just the sudden movement of tectonic plates. So when our tectonic plates move, they don't just slide smoothly past each other. I mean, these are big chunks of rock, and so they get stuck and they don't move for a while, and pressure builds up. Right? As the flows in the asthenosphere are pulling on these tectonic plates, trying to move them in different directions, and they get stuck and the pressure builds up until finally, something snaps and they jerk forward by a little bit. And that gives you an earthquake. That sudden movement, sudden release of that energy creates a shaking in the earth. And so when we look at earthquakes, we can identify what's called the focus of the earthquake. This is the location where the movement that the earthquake consists of originates from. So the spot where this movement is actually happening is called the focus of the earthquake. It's usually somewhere deep beneath the surface of the earth. So it's located along the fault line that separates our two tectonic plates. But it's somewhere deep beneath the earth where that movement is actually originating from. Then you'll also hear talk of the epicenter of the earthquake. The epicenter is just the spot on the Earth's surface that's directly above the focus. So the focus is somewhere inside the Earth. And if we draw a line straight up from the focus to the surface, that's the epicenter of the earthquake. And the epicenter is important, of course, because we all live on the surface. We don't live beneath the Earth like that. So we can locate the epicenter, and then the focus of the earthquake is somewhere below that. when we measure earthquakes, we can measure them according to what's called the moment magnitude scale. And this is a replacement of the older Richter scale. So it's pretty similar to the Richter scale. Some of the calculations are slightly different. You know, the term Richter scale has really gotten embedded in popular culture, so everybody knows that. But actual seismologists, people that study earthquakes, talk in terms of the moment magnitude scale. And what the moment magnitude scale does is it measures the amount of energy being released. So when you get an earthquake, when these plates move, you're releasing a huge amount of energy. And that's why earthquakes cause as much destruction and change of the Earth's surface as they do. You're releasing this huge amount of energy all at once. And so the moment magnitude is a number between 1 and 10 that tells you how much energy is being released here. And this is a logarithmic scale. So what that means is that every time you go up one number on the scale, you are multiplying the amount of energy released by 10. So a 5 magnitude earthquake has 10 times the amount of energy of a 4 magnitude earthquake. And then a 6 magnitude earthquake would have 100 times the energy of a 4 magnitude earthquake. Okay, so this is a logarithmic scale. Each time you go up a number, you multiply by 10 instead of going up by an equal increment. And another thing that's kind of illustrated by the chart that I have there is that you get a lot more earthquakes occurring at the lower magnitudes. So magnitude 1 earthquakes happen all the time. Like the Earth's constantly experiencing earthquakes of magnitude 1. But as you get into the higher magnitudes, they become much rarer. So a magnitude 8 or 9 earthquake is, going to be a once a decade kind of event, or even once every century kind of event, depending on where you are. So you get lots and lots of very small earthquakes, some of them so small that people can't actually feel them. You may have very little earthquakes that are picked up by a seismograph, by an instrument that's recording seismic waves, but that people are not actually even able to feel. But then, of course, the bigger ones are rarer, and we can feel them. We can see the destruction that they might cause. So when earthquakes occur, they involve a set of seismic waves that spread out from that focus. And there are several different types of waves, and these waves spread at different speeds, and they have different kinds of motion. So they'll have different sorts of consequences, and they'll move in different ways through the different kinds of medium that they're traveling through. So different types of rock, water, etc., that is conveying these waves. So I've got them here basically in the order that you would feel them if you are, some distance away from the focus of the earthquake. So the first wave that you would feel is the P wave, P for primary. And the P wave consists of compression and expansion of the Earth. So you get waves of squishing and stretching in the Earth. And these P waves can move fairly fast. So depending on the medium that they're moving through, right, what kind of rock they're traveling through, they can move up to 5,000 meters per second. That's kind of maximum speed. Most of them might move slower than that if they're moving through less optimal kinds of medium, but they can move pretty fast. And they're the fastest overall of our waves. The second set of waves that you'll get hit with are the S waves, so S for secondary. And so this is an up and down or side to side motion, right? So the P wave is expanding and contracting. The S wave is going up and down or side to side with your material, your Earth. And so these are going to move slower than your P wave, so you'll get hit by them second. Then the next kind of waves that you'll hit are the Rayleigh waves. And so they create a rolling kind of motion at the surface. So it's a lot like the way that waves on the ocean move. So if you were to look at a body of water like the ocean that's got waves going up and down on the surface, and you might watch like a buoy or a bird that's floating in the water, and it kind of goes up and down in these little cycles, right? And it's not moving forward or backward, it's just kind of cycling up and down like that. That's essentially what a Rayleigh wave is, but in the ground, in the Earth, rather than in ocean water. And so that's going to move slower than the S wave. And then the last wave that you'll get hit with is the love wave, which is a horizontal movement at the surface. So that's the slowest kind of wave to come along. So we've got these 4 different waves that occur at different speeds. And so if you're some distance from your earthquake, you'll be able to detect these waves separately from each other. They'll occur at different times. And so one of the cool things about these different types of waves is because they each spread differently through different sorts of media, through different types of rock that make up the Earth, we can use this seismic data to understand what's going on beneath the surface of the Earth. So there's a lot of stuff going on there beneath the surface that we can't directly see. We can't directly access it. I mentioned in the last lesson that the deepest that we've been able to dig, we're still in the crust of the Earth. So how do we know what's below that? How do we know about the mantle and the core and the asthenosphere and all these other things down there? Well, one of our big sources of information is seismic waves. So on this diagram, you see seismic waves spreading out from the epicenter of this earthquake, and they're traveling not just across the surface of the Earth, but the P and S waves are traveling downward through the Earth. And so they go through the Earth and come out somewhere on the surface elsewhere, and they can be detected by seismographs in other parts of the Earth. And so the speed and direction of these waves will get altered as they move through different sorts of materials. So for example, the S waves can't travel through liquid. And so you'll see there's this kind of a shadow on the opposite side of the Earth where you've got some P waves coming through, but the S waves don't make it. That's how we know we have a liquid outer core to our Earth. So by waiting for earthquakes to happen and then looking at the timing of the arrival of these different waves at recording stations in different parts of the Earth, we can get a sense of what kind of materials are these waves traveling through in the interior of the Earth. And that's how we can construct our understanding of the interior parts of the Earth that we can't actually go to and observe directly. So if we look at where earthquakes are occurring on the world, so this is a map of all of the earthquakes of 6 or greater moment magnitude from 1900 to 2017, and you'll notice that they make some nice lines. Right, we've got these neat little lines of earthquakes in these various parts of the world. And if you were to match this up with the tectonic plates diagram from last week, you'd see a real close correspondence. That these earthquakes are primarily occurring along the edges of our tectonic plates. And in fact, this is one of the ways that we can identify the locations of these plate boundaries, is looking at where are we getting lots of earthquakes. So that doesn't mean earthquakes can't occur away from these plate boundaries. In fact, we had an earthquake here in Pittsburgh about 10 years ago. But it was a small earthquake, and it was basically the only earthquake that we'd ever had in a very, very long time. Whereas if you're right next to a plate boundary, if we're in somewhere like California or anywhere else really on the west coast of the United States, you're going to get a lot more earthquakes. They're going to be a regular occurrence. You know, buildings will be built to withstand earthquakes specifically because that's a common enough thing to be worth the cost of that. So earthquakes occur primarily along these plate boundaries, and you can see that laid out very nicely on a map like this. So then if we look at the kinds of hazards that are associated with earthquakes, when an earthquake occurs, there's a lot of things that can go wrong. You get falling debris. People can get hit by stuff that we care about can fall and smash. Buildings collapse. We get damage to infrastructure, things like roads, electric lines, water pipes. All these things can get smashed and dislocated by earthquakes. We can get hydrologic changes. So depending on the kind of movement that we get, it can dislocate the course of a river. It can destroy either a natural or a human-made dam that's holding back a lake and cause a gigantic flood. It can crack open the earth and drain water off of the surface into underground. So there's a lot of hydrological changes that can occur as the result of an earthquake, and earthquakes can create tsunamis. And you see in the picture there the aftermath of the Boxing Day tsunami that hit Thailand and neighboring areas back in 2004. So you get this huge wave that is created by an undersea earthquake. And you may see in the news occasionally tsunami warnings that come out when an undersea earthquake is detected. If that earthquake happens in just the right way, it can create this gigantic wave in the ocean water that can smash into a coastline and cause a huge amount of damage to people, infrastructure, buildings, ecology, everything else that tsunami smashes into. So we've talked about some of the hazards that can result from volcanoes and earthquakes. But a volcano or earthquake by itself is not going to cause a disaster. And in fact, those of us that work on disaster research, my own research is mostly about forest fires, but there's general principles that apply to lots of different kinds of hazards. We often say there's no such thing as a natural disaster. So that expression natural disaster that we often hear, that's not really what happens. Because a disaster is the loss of things people value. So lives, health, property, community, things in the environment that we care about. When we lose those things, when they're destroyed in some sort of event, we call that a disaster. Because if you imagine a volcano erupting on a remote, uninhabited island, no matter how big that eruption is, that's not going to be a disaster. If there's nobody there to be damaged by it, right? There's no people to be killed by it. There's no buildings to be destroyed or anything like that. That's not a disaster. It's just a thing that happened. So a disaster requires people and the things we care about to be in the path of some sort of a natural event. So as you can see in the little diagram that I've made there, disaster occurs at the intersection of a hazard event. And the hazard event may be totally natural. Right? It could be an earthquake, it could be a volcano, it could be a forest fire, it could be a hurricane. There's all kinds of natural events that are hazard events, but they don't become disasters until they intersect with vulnerable people and things that we care about. So there has to be somebody or something that we don't want destroyed in the path of that hazard. And the fact of people and things we care about being in the path of that hazard event is the result of some sort of human choices. People have in some way decided to place themselves and their valuables in the path of that hazard. People decide where to live, how to build, how to distribute resources. All of these things will determine what kind of a disaster might arise from a particular hazard event that might occur. So we get a really clear illustration of this in the case of earthquakes. From back in 2010, we had two major earthquakes in the Western Hemisphere. So we had an earthquake in Haiti that was a 7.0 moment magnitude earthquake. And it killed 230,000 people. So this was a devastating earthquake, enormous loss of life in Haiti. The effects of it are still being felt even today, over a decade later. So it was a massively destructive earthquake. That same year, we had an earthquake in Chile that was an 8.8 moment magnitude. And so if you remember, the moment magnitude scale is logarithmic. So an 8 would be 10 times as much energy being released as a 7. And then a 9, 8.8 is almost 9. A 9 would be 100 times as destructive as a 7. And so this was a much bigger earthquake as measured by the amount of energy that was being released from that earthquake. And yet, this earthquake in Chile only caused 531 deaths. Now, obviously, that's still a lot of deaths. That's still a major tragedy. But it was a much smaller disaster than the disaster in Haiti, even though the earthquake was a much bigger earthquake. And that's because of the vulnerability of people in these two different countries. Haiti is an incredibly poor country. Their infrastructure is not very well built. Houses just collapsed on people as that earthquake happened because they were not built very well, because people couldn't afford to build them well. A lot of people were living in very vulnerable kinds of areas on steep hillsides and stuff that collapsed under the shaking of the earthquake. And once the earthquake happened, people didn't have the resources easily to hand to reconstruct from the earthquake, to rescue people that had perhaps been trapped by falling debris, to get food and water and shelter to people that were affected by this earthquake. On the other hand, Chile, though not quite as well off a country as, say, the United States, Chile is much more economically well off than Haiti is. And so the buildings in Chile were built to a much higher standard. They were built to withstand earthquakes, so they were less likely to collapse and kill people. Chile had a much better medical system in place, ready to help people that had been harmed by the earthquake. They had the ability to get resources to people much more easily. So the people in Haiti were much more vulnerable to an earthquake than the people in Chile were. So Haiti suffered a much bigger disaster, despite the fact that the hazard event, the earthquake itself, in Haiti was significantly smaller than the one in Chile. So we have differential vulnerability between different places and different groups of people. And as a general rule, the people that are already worse off in society as a whole, so the poor, women, racially marginalized people, etc., right? The people that are already not doing as well in society tend to be the ones that are also most vulnerable to hazards of all different kinds. Right? So the poor, for example, will be more harmed by an earthquake or a volcano or a forest fire or a hurricane, etc. So this means that if we're concerned about disasters resulting from events like volcanic eruptions and earthquakes, we need to be concerned not only with the physical science of how plate tectonics works and what's going to cause earthquakes and those kinds of things. We also need to be concerned about the social side of things. Who's living in the path of these kinds of events? What kind of resources do they have access to help them if one of these events would occur? So this is a good topic to bring together your natural science and your social science understandings. And so I won't go too much deeper into the social science aspect of that, since this is our natural science class, but I want to flag that connection for you because I think that's an important one of understanding how the things that we learn about in a natural science context and the things that we learn about in a social science context are connected. So for your lab assignment, you're going to be looking at that Yellowstone hotspot that I mentioned earlier. And so our goals for that assignment are first for you to be able to evaluate information about these kinds of tectonic hazards, right? To find reliable information and cut through any false information that tends to circulate online about some of these kinds of hazards. And then second, to consider possible social responses to these kinds of hazards. So if we're going to have things like volcanic eruptions and earthquakes, well, what do we do about them, right? How do we help keep people safe from these kinds of hazards? So that will be your lab assignment. So you can move on to working on that.